Welcome to ScalaUA.
Let's start probably. So I'm happy to see you here, and today we'll speak about some kind of abstraction creation things. It's recursion data schemes and some hacks around of it. But first of all, I want to introduce myself. My name is Artur. I'm writing little bits of my code in Scala already for 3 years. Currently I'm working in Scala24 company, and what we are doing, we're creating leading platform for selling used cars in Europe. We do it on our stack with microservices, Kafka, Play, Yaka, and so on. And we do it in autonomous teams. We build we run what we build. So if you're interested, we are currently hiring, relocating to Germany and so on. So contact me or open GitHub link on the slide. Small remark: we will speak about a little bit freaky stuff, and it will be useless in your day-to-day job, because probably most of the time you create some features for customers, and this one stuff is related to creating nice abstraction for libraries, and it will not be used by your customers as guys who pay money. It will be used by us developers. So in case of WTF, just know that I warned you. So recursive schemas. Recursive data schemas, it's not so complicated topic at all, and you probably work with this in your day-to-day job. So in Scala, a good example of recursive schemas is just list. List contains some two subtypes as const and nil. And why it's recursive schema? Because inside of const you can put another instance of list like const or nil, and you can nest it wherever you want. It's infinity. But it's not only about collections, it's also about file system and databases, and probably you will find it in everything that's created for developers, because like it's very it's very good a good way to abstract your code base, to hide all the implementation and provide really good API for us developers. So let's find problem on our head. Mostly when speakers talk about it, what they do, they say, okay, we have some, I don't know, arithmetic expression, and let's evaluate it in one more freaky way. Let's create a lot of classes and evaluate this mathematical expression. It's useless probably. So I will tell you a story. It's from my real project. One day, some product guys come to us and say, okay, we have a system and we want to implement some filtering, searching on top of the customer data. We say, okay. And they say, hey, maybe it will not be so complicated and you will do it fast. We say, maybe, but then we remind that we have all our data in a very denormalized way. We have bunches of events, so it will be quite hard to search in this data. And we understand that we will need to add to our infrastructure something like Elastic and so on, and it will take a lot of time, because like nobody did it before. And product guys say to us, okay, we need MVP as fast as possible. We need to check idea, and just do it like as you can, without all this index in Elastic and so on. We don't care about it. We just want to show it to a couple of our customers, and if it will work, we will implement it fully. But like in our team, we have no culture to write code and then put it in trash can and rewrite from scratch. So we understand that we need some abstraction to have possibility to write queries, and then evaluate these queries in different backends. And that's completely the case in which one I want to explain you how you can work with the recursion schemas now. So first of all, to define some API, we need to say which one actions we will support. For our case, we will support just equals and or. Like, we don't need some complicated logic, we just need to understand principles. Next one, we need to create some kind of API. So it will look something like that. We will have co-product of expression and products as equals and or our actions that will point to another expression. We need it to have recursion, and we will have some value classes that will be required not only to put real values inside our tree, but also to validate which one data all the developers will put into our tree, because in another case they can put whenever they want, and when we will try to interpret it, we will have a lot of runtime errors and so on. Okay, so currently we have our ADT and we can use it. On this step, developers can write all these queries that are required for real products. And it's not looking so complicated, it's just tree of nested expressions. And now we have it in all our code base. And what we want, we need to find a way to evaluate it somehow. And in this not so complicated example, evaluator will be something like recursive function, where we will convert from expression to string. String will be, in our case, it's some secure query. And if we're talking about value classes, it's just converting to string of our real value. If we're talking about actions, what we need to evaluate pointer on expression. And this is exactly a problem of that, but we'll talk about it a little bit later. So currently we are going into recursion to evaluate all expression one by one down to the bottom of our expression tree, and then get back with full string of requests. We can do the same for another cases. For currently we will evaluate not secure query, but query for just some programming language. And you can write these interpreters for wherever you want, for some query builder, I don't know, for every object that you want. And it probably will work. It will look like this. We will pass this expression to our evaluate function. It will return us the strings compiled. And like everything good, we can go home, drink beer and so on, but we have a very big mess in our interpreters. We must evaluate our expression every time. It means that we must copy-paste logic of traversing over our structure from interpreter to interpreter. Why it's a problem? Because interpreters, it will be not only one interpreter, so it can be a big amount of it. And also, if you will try to partially interpret your tree, you will fail. For example, in current case, I want to do some like simple optimization. If one of or nodes already interpreted is Boolean value true, probably I don't need to calculate all expression inside my OR. I just need to replace this OR with true. It's already computed. And problem that in that case I cannot just say, okay, in other cases just put other. Why? Because inside every my action I have pointer on another expression and I need to traverse over all collections. So for every function like this, I need to define how I will work with every action that I have. For and, for equals, and so on.
Why can you do it as partial function?
It's already a partial function.
Mm-hmm. Yeah. Yeah. Sorry.
Okay. So let's think a little bit how we can improve. First of all, we have a problem that we must traversing logic with our interpreters. And let's think how we really want to interpret our data. Probably we don't want to operate with pointers on expression, we want to operate with already evaluated data inside our actions. So, for example, AND will contain not sequence of a expression, but sequence of already evaluated queries. To do that, and not to change our API fully, we must do something like generics. Let's try to generalize our expression tree and say that, okay, instead of pointers on some expression, we will point on something. Something we don't know what about, to what we will point later. Okay. After the change, we can write a little bit cleaner interpreter. Now, as you can see, about value classes, nothing to change it. But if you will take a look on action classes, in expected we already have evaluated value, it's already string. And in that way, we don't need to write here how we will traverse over our expression. You don't need it. So we fix one of the problem. And our tree is, like our DSL is not changed. But now I have a question. Who thinks that currently we are in big trouble after adding generics? One man. Okay, I will help you. Let's evaluate types. So what's going on? Currently, our compiler cannot be sure that we have same type recursion. Before it will be sure. It was sure that, okay, inside expression we can have only expression. Now inside expression we can have everything, and we must show compiler that okay, we really have only expression inside of expression inside of expression. Why is problem? Probably what you will need to do with this expression is to put in some function to evaluate it. And now we have a question: which one type of parameter we must set? The only one way to process data like this is to say, okay, we accept expression of any, lose all types, and it's not our case. So we come to topic of small type hack. Guys called it fixed point data types. So if we will forget about all these type systems and so on, just imagine that we have very big numbers and we want to compare it. And probably we don't really care about all the numbers in right side. We care about a couple of numbers in left side. And what we will do, we will put point somewhere and say, okay, we will put point on 8 digit. And after that, we will forget about everything that on the right side of the point, because currently for us it's unnecessary. And we will operate only with left side. But we will not forget about right side. We will get it back a little bit later. Probably we can do the same with our types. Why not? So this one is implementation of this hack, and I will try to describe you how it works. Because first time when I looked on it on presentation, I just have a feeling like, what the fuck, how it works. So we have some case class fix, and it operates with generic type with a whole. For our example, you can just understand that this generic type with a whole, it's our expression of t, and what we will put inside. And inside of this fix, what we want to put, it's expression of t, where t will be already fixed expression. By the way, by this way, we can prove to compiler that inside of our expression we will contain only another expressions, nothing another. So let's try to take a look on it a little bit deeper. So first of all, this comment is just how our type will look on as a result. It will be just fixed expression. So probably we have some AND action, and that contain some n expressions. And if we will try to resolve type, it will be something like expression of any or something like that, so we don't care. And let's try to fix it. Let's try to just wrap it to fix, and our compilation will fail. It will fail because if you take a look on unfixed notation again, we must, inside of fix, we must have expression, and that will contain another fixed expression. So what we need to do, we need to fix, or wrap in fix every expression inside again and again, until we will reach bottom of our tree. We must wrap everything. And if when you take a look on AND action or action where we have pointers to some expression, it looks logically, we just wrap our pointers into fix and it works. What we can do with value classes? Value classes have this generic type too, but they don't have any pointer. So currently I have a question. Do we have any restrictions to just say that our value class will have generic type fixed expression? Like, who thinks that there are some restrictions and we cannot do it? Okay, so because we don't have any fields that must have this type, we can say that generic type of string value can be unit, user, option, or fixed expression, wherever they want. Compiler don't need to prove anything. It will just work. And after some changes, we can a little bit fix our problem. We will say that, okay, we have some type alias logical expression that will be the type of fixed expression. We will fix all the nodes of our tree, and we will be able to operate with it. But I don't think the developers will be really happy to write these fixers all around their code base. So let's do it a little bit cleaner. Now we hide all this complexity under the builders, and our expression looks really nice. So it's just fancy builder. Okay, currently we resolve a problem with clean interpreters and these little problems with types. And in previous step we draw it out traversing logic out. So now is the time to find this traversing logic again. And one question for us. Just imagine that you want to apply some function to every object inside your collection, tree, hash map, and so on. Which one function you will use in Scala?
Map.
Map. So probably we need to design our own map function for our custom data structure, and like it's good that we have a functor. Functor, it's some kind of basic functional abstraction, and to implement functor, we must just define the function that will get some data container, get function from A to B, and it will apply this function on data inside container and resolve modified data, modified container. Nothing complicated, you use it every day in Scala. So how we can do it in some proper way? We can use a library of functional primitives, Scalaz, cats. It probably will be the same in both of it, but here I use Scalaz. So in current example, we have some container, data container for T. We create functor. Functor is Scalaz trait that contain method definition of map. So when we write new functor container, our IDE will tell us, okay, you forgot to implement .map. And we say, okay, generate for us this method. It will generate for us definition of method. And then what's left is just to implement it for container. All that we need is to get data from container, put it as parameter in our conversion function, and wrap it again in container. Done. We implemented .map function. But in our case, is not so easy as that. So if we want to evaluate functor file expression, what we need to do is to do pattern matching on different variants, different products of our expression per product. So in case of value classes, there is nothing complicated. We just need to recreate it again to satisfy type rules, because before we had string value of type A, now we want to have string value of type B, so nothing can change it. And for actions, we must apply this function f for every pointer for equals and just wrapping expected value in this function. And for expression, we must run this function to every nested expression inside. So currently what we achieved, probably when we will work with our structure, we will unfixing it one by one. We will open this like box with cookies. We will open one cookie, second cookie, third one cookie. And our function, our f, will be created to operate with another expressions. So we will recursively go to the bottom of our tree until we will reach the end. It's probably what we need, because after that we want to use our interpreter to interpret our tree from bottom to get bottom value of our tree string value, create from it query, put it in upper value, create from this upper value query, and go up until we reach top. And in that moment we will have fully interpreted value. And now let's take a look at our task a little bit globally. If we imagine that we work in some categories, probably our expression tree is some kind of one category. If we want to reach another category of our query, elastic query, secure query, wherever we want. And we need some arrow from first one category to second one. And this arrow called morphism, and what we really need is folding, because we want to fold a lot of values into one query. There is some weird name is catamorphism, and if we will talk on human language, it's just generalized folding operation. It's when we just get rid of all specific logic and have definition of folding operation. It was introduced by Eric Mayer. If you passed course on Coursera about Scala, probably you know it. It's a guy in really funny t-shirts, and he had a white paper. You can see the name on the slide. And here's a lot of different morphisms, but we need only catamorphism. So, kata, what? Kata is some function that operates with, as you see before in fixed notation, it's operate with generic with a whole, without expression of t. And result type t. For current example, we just string. it got expression, our expression that we want to evaluate. It got functor. Functor is the way how we will traverse over our structure. And it got interpreter, just our function that will describe how we will convert from expression tree to query. And then, if you look on implementation, probably we need to start reading it from center, because first of all, we want to open our cookie box, open first one expression, and recursively use function on it. So go inside of it. On every step, we will go deeper, 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 and deeper. And then when we will start go back, we will use our interpreter to do whatever we want to build our expression. So, as a result, we will have our starting expression rewritten on our some kind of DSL, and we will use our kata function. We will put inside expression functors that we defined it already, algebra, and it will generate us the same as we see in first slides. But what we achieve now we delimit everything, and it provides us more freedom, and I will talk about it a little bit later. We achieved extra profit. Now it's not a problem to write partial interpretation of our tree. So currently we do the same. If our OR expression contains one expression that's already validated as true, probably we can replace it. In other cases, we can just return other. Why? Because all our traversing logic is in functor. We don't care. No more pain with copy-paste code. And if you not feel happy to implement all this function by your own hands, here's guys from Spam Data who already implemented library for working with stuff like that. It's called Kushka. And what they do, they provide to use this fixed point hack notation. They provide to use some type aliases. For example, currently we have some type algebra that contains expression in string, and it means exactly the same that we see before. It's converter from expression string to string. And it provides us all this katamorphism, diegomorphism, and so on, all these morphism operations out of the box. So we just import syntax and use it. It will work the same as things that I showed before. So if you're really interested, you can take a look at the library, there you go. So, we reach the line when we, first of all, can easily extend our API. What we can do, we can add a new variant of action, and after that, what's left is just to handle it in functor and handle it in our expression. And the best part of it is that if you forgot to handle it in some of this matching function, you will get Scala warning during compilation. If you enable some flags, your compilation will fail, and you will take a look at it and I forgot about some place to implement logic of handling. Okay, you have no any copy-paste logic. All the logic that you define it exactly in one place, and that means that it's bug-free. So you can partially evaluate and don't care about some actions that you don't want to handle. It's easier. And everything is hidden under abstraction. Your customer, your developers will see only this ADT, only this actions tree, and function that accept this tree. That's all. After that, they will just evaluate it, and backend will be chosen on your library side. They don't know anything about how it works. Also, what is cool is that if you develop your library and you want to have some contributors, probably in one day some guy come to you and say, okay, I have some appropriate index storage engine, and you probably don't want to support it. You will say, okay, you can write your own implementation for it, and except of giving him diving into your library, you will just say, okay, please implement this function, and that's all. I don't need from you anything. Just do this mapping from my type of tree to your type of tree. Done. Okay, but there are still some things that could improve. First of all, we can add some types to our DSA. Here you can see that I add to expression equals some type of user, and with the first parameter, that it's just a pointer to some fields, we can calculate second parameter type. And with this type, we can provide some implicit converters, for current example, from string to string value, from just string of Scala to string value of our tree. And also we can get name of fields by macros from this definition. So it will be a little bit better, because if you will use refactor of IntelliJ IDEA, it will rewrite it in every expression, and you will not need to use some hidden paths and searching for first name. So also you can improve it a little bit more and add syntax like in Sneak API. So if you ever use Slick, they have quite common syntax that looks like just general operation in programming language. And also, if you want to operate with really big trees, what you can do, you can get rid of recursion. You can rewrite your folding based on traversing on tree in depth, and it will work if you will have really big trees and you will not get Stack Overflow. So, it looks like we reached the end. Thank you for attention. Any questions?
I miss probably the most important part of the presentation. I mean, I don't understand why you still have to add the types to your expression tree. Why? Because maybe I need to explain this more.
Okay, it's not a problem. So you're talking about 1 minute. You're talking about this step, yeah?
Yes. Why this type needs to be added? Because you saw later on that you need it for tree traversal and optimizations.
No. It started from idea that we need clean interpreters, that we don't want to have pointers on another expression inside our interpreters. So currently, we want to operate with already evaluated data inside case classes. So inside equals, we will have field that was string before, and we will have expected that will be already evaluated value inside, not a pointer.
Okay, now it's more cleaner, but I'm still convinced. Maybe we can talk later on.
Okay. So, thank you.
Well, the ScalaUA for me, it's a really good place to get in touch with Ukrainian Scala community. I really like to come here. I'm here the second time, and topics here are always really cool. So I recommend it for everyone.